Good morning. Welcome to TMMS Productions, ICSE Physics for Class 10. Today we are going to review current electricity. Point number 1. Charge. The SI unit is 1 coulomb and 1 coulomb corresponds to a deficit of 6.25 into 10 to the power 18 electrons. 2. Current. Now current is the rate of flow of charge, and so our formula becomes I is equal to Q upon T. Unit wise I will be 1 ampere, Q will be 1 coulomb and T will be 1 second, and so you'll have 1 ampere equal to 1 coulomb upon 1 second, that is 1 C per S. Now these ones are all objective questions, fill in the blanks, etc. that you have to be ready with. We come to potential and the potential difference. V, which represents the potential or potential difference, it is W upon Q, where W is the work done and Q is the charge that is being transported from one point to the other or from infinity to the given point. And if we substitute this as 1 volt, work done as 1 joule, and Q, the charge, as 1 coulomb, then we have 1 volt equal to 1 joule upon 1 coulomb, which is 1 J per C. And that gives us the definition of 1 volt potential. So we say that 1 volt is the potential when the work done is 1 joule in moving a unit charge, that is 1 coulomb charge, from infinity to the given point. And if it is potential difference, then we say 1 volt is the potential difference when the work done is 1 joule in moving unit positive charge, that is 1 coulomb charge, from one point to another in the conductor. That brings us to point number 4, which is Ohm's law. Ohm's law is important at all times. And so Ohm's law, the statement goes, the current flowing through a conductor is directly proportional to the potential difference across its ends, provided the physical conditions and the temperature of the conductor remains the same or remains constant. So that brings us to another question based on Ohm's law. First one will be the statement of the Ohm's law, and the second one will be the expression of the Ohm's law. So we have V is equal to IR. This becomes the expression or the relation that is derived from Ohm's law. This will lead us to R equal to V upon I. And so if we substitute the units, R is the resistance which is measured in ohm, and we have R equal to 1 ohm, V will be 1 volt and I will be 1 ampere. So we'll have 1 upon 1 will give us 1, and that will give us the definition of 1 ohm resistance. So we say that 1 ohm resistance is the resistance of the conductor when the current of 1 ampere is flowing through the conductor at a potential difference of 1 volt. Point number 5 is where we look at the graphs. Now graphs is where you can have applications. Now first one is I against V graph, and the second one here is V against I graph. Now I'm going to take V against I graph first, and in this I'm going to say the slope is going to be equal to delta V upon delta I. And so V upon I gives us resistance, so slope represents the resistance. Here we will have slope. On the other hand is delta Y upon delta X, which will give you delta I upon delta V, which will give us the reciprocal of this, which means it is 1 upon R, and that becomes the conductance. So you need to know which are the quantities represented by the slopes. For the second one, here the slope is going to be resistance. Point number 6. Let us say that we have been given a graph and this is an application question on Ohm's law. On y-axis there is V and on x-axis there is I, and we are having two graphs over here. One is T1 and the other one is T2, and the question says which one of T1 and T2 is higher temperature. Now for this, what we would do is just take a line drawn from the given PD parallel to x-axis, and we will drop the perpendicular and we'll call this current in 2. And here where it cuts T1, here we will call this as current in 1. Now you can see from the graph that I2 is greater than I1. So we shall mention that I2 is greater than I1, and therefore we will have the resistance of 2 and the resistance of 1 will be comparable. If I2 is greater than I1 and R1, they are inversely proportional to each other, and so R2 will be less than R1. And here we will mention, since R proportional to 1 upon I, they are inversely proportional quantities. More the resistance, less the current. Therefore, temperature wise, now since we have to find out the temperature comparison, we will have T2 and T1. These will be the two temperatures. Now resistance increases with increase in temperature, and so if R2 is less, T2 also will be less, and here we will say since R is directly proportional to temperature, and so you will see therefore T1 is greater than T2, and therefore T1 is higher than T2, and that is our answer. Let us come to the 7th point. Here I am taking another application of Ohm's law. Here again I have shown the graph, and then again there are two graphs A and B. This is voltage and this is your current. Which one of A and B is in series and parallel? Which one represents series connection? Which one represents parallel connection? Here again I shall draw this, and here I will show this is the current in B and this one is going to be the current in A, and from the diagram I can see that IB is greater than IA. Therefore, the resistance in B is going to be less than resistance in A, exactly the same way as we did in the earlier question. And here we will say again resistance and current, they are inversely proportional to each other. And now understand that if resistance of B is less, then therefore B is going to be parallel connection, and A is going to be series connection. And the reason for that is that in parallel connection resistance is less. The equivalent resistance becomes lesser than the least, and here the resistance in series is more because the equivalent resistance is higher than the highest individual resistance of the combination. Let us come to the next point. Now here I have shown two graphs. You can see the first one is V against I, a straight line graph, and the second one is V against I, which is a curve, and they will ask you which one is ohmic, which is non-ohmic, and if it's a straight line, remember it is ohmic, and this one will be non-ohmic. And the reason being, here you will have a straight line graph, and so your slope is going to be constant, and therefore slope is going to be the resistance is going to be constant for the ohmic conductor, and here it is non-ohmic, so it will be non-ohmic, where you will see that the slope at each point is going to be different, because you will see that the theta at each point is going to be variable, and so resistance is going to be variable, which means resistance is not constant and therefore it is non-ohmic. Let us come to point number 9. Prepare the question like comparison between ohmic and non-ohmic resistance. Make the column and learn. These ones are, most of the textbooks will have these differences written. You have to just learn them by heart. We come to point number 10. Factors affecting resistance of a conductor. Number 1 is material. So it depends upon the material, which ones will have free electrons more, which ones will have less. Accordingly, the material will have less resistance or more resistance. We come to length. More the length, more will be the resistance. So resistance is directly proportional to the length. The thickness means it will offer you the area of cross section. More the area of cross section, less the resistance, and vice versa. So resistance is inversely proportional to the area of cross section. And for temperature, more the temperature, more will be the resistance, and here we will have resistance directly proportional to the temperature. Now we come to number 11, which is specific resistance or resistivity. Your formula is your resistance directly proportional to length, inversely proportional to the area of cross section. And so we have the constant of proportionality. This rho is the specific resistance or resistivity. So R is equal to rho into L upon A. Therefore, rho is equal to R into this comes this side. So it becomes A upon L. Now unit wise you will see that for resistance you will write ohm and multiplied by here area of cross section. In SI unit it will be meter square and length will be meter, and so you will have ohm meter. That will be the unit of specific resistance or resistivity. That brings us to the next point, which is choice of material. Now this one over here, this is all for give reasons. And so they will ask you objective questions. What will be the choice of material? But also they'll ask you why would you choose that. So the first one is for conducting wires, we'll use mostly copper because it has low resistivity. And so it allows more current to flow through. Number 2 is resistance wires, that is standard resistances, that is made of manganese or constantan. These alloys, their specific resistance or resistivity is high and it remains constant with the change in temperature. The filament of the bulb is tungsten since it has high resistivity and it has high melting point also. Then we come to the heating appliances. In heating appliances, the heating element is mostly made of nichrome. Nichrome reason, it has high resistivity and it increases with temperature. The last one here is fuse wire, and that is the solder material, which is 50% lead and 50% tin. And reason is since its resistivity is low and it has low melting point, so it will easily melt and break the circuit in case excess current flows through the circuit. Let us come to the numericals. Now numericals, the first one, that is A, calculate the current flowing through a wire of resistance 10 ohm connected to a supply of 2 volts. Now first of all, understand the quantities that are there, 10 ohm and then we have 2 volt. And so we shall write R is given as 10 ohm, your PD, that is V, is given as 2 volt, and they are asking you the current is how much. And so we'll use the Ohm's law equation, that is V is equal to IR by Ohm's law, and therefore we will have 2 volts will be equal to I multiplied by 10 ohm, and therefore I will be equal to 2 volt upon 10 ohm, which is 0.2 ampere. That is our answer. Let us come to B, the second numerical. A wire of resistance 3 ohm is stretched to double its length. Find its new resistance. Now, if you look at this, there will be two situations. Your first situation where it will have its length L1, and now it will have length L2. So if my original is length L and my L2 is 2L. Reason? It is stretched to double its length. Now, if you stretch it, your area of cross section is not going to remain the same. What will happen to it? If earlier it was A, then now it becomes A upon 2 because you have stretched it to double. And your R1, that is resistance, is 3 ohm, and you have to find R2 equal to how much? And so I'm going to show the solution here itself, this side. We know that resistance is rho into L upon A. And so we will have R1 upon R2 will be equal to L1 upon L2 into A2 upon A1. So we substitute here 3 ohm upon X because we have to find this. Now L1 is L, L2 is 2L, multiplied by A2 is A upon 2, and A1 is A, so we are dividing by like so. And so when you cross multiply, X will be equal to 3 into 4, that is 12 ohms. So that is going to be our new resistance. And that is our answer. Number 14, electromotive force. That is simply called as EMF. Now EMF is defined as when there is no current drawn from a cell. That is when the cell is in open circuit. Then the potential difference between the terminals of the cell is its EMF. Now here in the open circuit, we have to talk about the work done between the terminals of the cell, that's in the external circuit, as well as the work done when the charge is passing through the electrolyte in the internal circuit. So it will be the work done in the external circuit as well as the internal circuit. Terminal voltage is defined as when the current is drawn from a cell, when the cell is in a closed circuit. The potential difference between the electrodes of the cell is known as the terminal voltage. And so we talk about terminal voltage only when we talk about the external circuit. So when the cell is in use, mostly we will have the situation where we will see drop in potential, that is E minus V, which is EMF minus the terminal voltage. So our 16th point is drop in potential, which is EMF minus the terminal voltage. And then we come to number 17, which is comparison between EMF and the terminal voltage. We have to learn these differences. They will be available in any textbook. We should know it by heart. We come to 18th point, relation between EMF, terminal voltage and the internal resistance. And here we will have number of formulae, but the most important one are this one where we have I equal to E upon R plus R. E is the EMF, this is the current, and this is the external resistance or resistance in the external circuit, and this one will be small r, which is the internal resistance. Also, we will have E minus V equal to IR. Here again we take the internal resistance. Point number 19 is internal resistance and the factors affecting it. So internal resistance is the resistance offered by the electrolyte of the cell, and the factors affecting the internal resistance are surface area of the electrode. Larger the surface area, less is the internal resistance. Then the second one is distance between the electrode. More the distance, more the internal resistance. Nature and concentration of the electrolyte and the temperature of the electrolyte. Now we have to know these factors well. We come to combination of resistances. As you remember, it is in series. They are placed end to end, all these resistances like so, and in parallel they are kept like this, where all the positives will be together one side and the negatives will be together one side like so. So this will be the diagram for the parallel combination, and the equivalent resistance for the series will be RS. Which one will be sum of this? So it will be R1 plus R2 plus R3 like so. If there are any more, then you have to just keep adding them. And so as a result, the equivalent resistance in series is greater than the greatest individual resistance. And so if we want to increase the resistance, we will combine them in series, which means we will get lesser current. More the resistance, less will be the current in the circuit. Now we come to the parallel combination. So we have equivalent resistance will be 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. And so in parallel, the equivalent resistance decreases. It is lesser than the least individual resistance. So when we want to decrease the resistance in the circuit, we will connect it in parallel, which means the current will increase in the circuit. Now we come to another one here where we have the simple circuit diagrams where we have to calculate the equivalent resistances. So the first case that we have, case A, we have between X, you can see this is 4 ohm, and then we can see this line with 2 resistors in series, and here this line like so, this is in series, and this line and this line, they are going to be in parallel. I'll call this point as point A and point B, and so between A and B, the 2 resistors here, they are in parallel, and then in turn it is connected in series with Y. So now if we have to find the equivalent resistance between, let us say, A and B, and the second case X and Y, then the first part where we talk about between A and B, look at the diagram 1 and 3. These 2 resistors are in series, so I'll call that as RS1. So I will say RS1 is equal to 1 ohm plus 3 ohm, which is equal to 4 ohm. And these 2 again, can you see this is only one path here, and so that will be my, I'll write this as RS2. So RS2 is going to be equal to 2 ohm plus 2 ohm, which is 4 ohm again. Now you will see that RS1 and RS2 are in parallel because they are in 2 branches like so. And so you will say, therefore 1 upon Rp will be equal to 1 upon RS1 plus 1 upon RS2, which in turn will give me 1 upon 4 plus 1 upon 4, which will give me 2 upon 4, which is 1 upon 2, and therefore I shall write it this side. Therefore Rp has come out to be 2 ohm. You do reciprocal of this. So now we have Rp is here between A and B. Therefore equivalent resistance between A and B is equal to Rp, which is 2 ohm, and that is our answer 1. Now let us come to the second part. In our second part, we need to find the equivalent resistance between X and Y. So you will see X has this resistance, and this resistance. Now this one you have to take it as Rp, which is 2 ohm. So you have to consider this as 1. And so this, and this, they are in series. So we will say 4 ohm comma Rp comma 6 ohm, that is 4 Rp and this, are in series. Therefore equivalent resistance between X and Y is equal to 4 ohm plus 2 ohm plus 6 ohm, and so that is equal to 12 ohm, and that is our answer 2. Let us look at some more questions. Calculate the equivalent resistance between, and we have here case 1 here and case 2 here. Now you will see that there are number of resistors here between AB and CD, and we have to find the equivalent resistance. So whenever you are looking at a circuit diagram, see if one of the ends is having the current coming through the wire like so. It will split into 2 paths. This is one path and this is the second path. So you will see that 4 ohm and this 4 ohms, they are having just one path for the current, and so they are now connected in series. I'll call that as RS1. So RS1 will be equal to 4 ohm plus 4 ohm, that is equal to 8 ohm. Now this resistance of 8 ohm and this, they are in parallel. So we will mark the circle round like this and we'll call that as Rp. So now Rp is going to be found out using the formula 1 upon Rp is equal to 1 upon 4 plus 1 upon 8. And so our LCM is going to be 24. And so 4 goes 6s and 8 3s. So we will have 9 upon 24. And so you will have Rp will be equal to 24 upon 9. So 3 8s and 3 3s. So we will have 8 upon 3, which will be 3 goes twice and 2/3 remains, so 2.67 ohm. This is the value of your Rp. Now let us look at the diagram once again. So this full thing here, this is going to be equal to 2.67. Now from C, this 4 ohm and this Rp and this 4 ohm, they are connected in series. So we shall write that, we shall say the equivalent resistance between C and D is going to be equal to 4 ohm plus Rp plus 4 ohm, which will give us 4 ohm plus 2.67 ohm plus 4 ohm. That will give us 4 and 4, 8 and 2, 10. 10.67 ohm. And that is our answer. Now in between where we have found is 2.67, this is nothing but it is equivalent resistance between A and B. So I shall write that here. Now let us look at our second situation. Now again we will have the current going from one end of it. It will split into two branches, and so you will see this is going to have one path, so it will go like this. This is going to be your RS1, and so you will say RS1 is equal to 4 ohm plus 4 ohm, which is equal to 8 ohm. Now this 8 and this 4, they are in parallel, so we'll just write it a little differently than the earlier question. Equivalent resistance between A and B is going to be RP because they are in parallel, this one and this one. And so we will have 1 upon RP is equal to 1 upon 4 plus 1 upon 8. And we already know the calculations here. Therefore, we will have RP equal to 8 upon 3, which is again 2.67 ohm, and that could be our answer 1 if they ask us the resistance between A and B. And now we will come to the equivalent resistance between X and Y. So we will have equivalent resistance between X and Y will be equal to 4 ohm plus RP plus 4 ohm, which is equal to 10.67 ohm, and that is our answer. Let us look at some more situations here. We have to find the equivalent resistances between this end and this end. And so we are going to have the current passing through here just to see how many paths are there for the current. This is one path and this is another path. So I will keep this together, and this is going to be my RS. So my RS is going to be equal to 4 ohm plus 4 ohm plus 4 ohm, which will be 12 ohm. And then this 12 and this 4, these two are in parallel between this end and this end and this end. And so I will say RS and 4 ohm are in parallel. Therefore, 1 upon RP is equal to 1 upon 4 plus 1 upon 12. That will give me, LCM is 12. So 3 plus 1 that will give you 4 upon 12, which is 1 upon 3, and therefore equivalent resistance is equal to 3 ohm, and that is our answer. Now, if you look at this diagram, it's exactly the same, except that the current is passing from here and coming out from here, or the other way. Let's do it this way. The current is passing, going through this branch and coming out. And so as it goes through this branch, how many resistors are here? This is one, which I'll call as RS1, because they are in series. It's one path. And here this is another path. So this is my RS2. Let us write down RS1 will be equal to 4 ohm plus 4 ohm, which is 8 ohm. RS2 is again 4 ohm plus 4 ohm, which is equal to 8 ohm. And RS1, this branch and this branch, they are in parallel between these two endpoints. So RS1 and RS2 are in parallel. Therefore, 1 upon Rp is equal to 1 upon RS1 plus 1 upon RS2. That gives us 1 upon 8 plus 1 upon 8, which will be 2 upon 8. That gives us 1 upon 4. And therefore, equivalent resistance is equal to 4 ohms. And that is our answer. Let us look at one more circuit diagram. So we have a cell with EMF 20 volt. Small r means internal resistance 0.6 ohm. This is the key ammeter 2 ohm resistance, and it is connected with the parallel circuit having 6 ohm and 4 ohm, and it completes the circuit like so. The first part, we are asked to calculate the resistance in the parallel circuit. So let us start with our answering. The first part. Six ohm and 4 ohm are in parallel. I'll just write like so. Therefore, 1 upon Rp is equal to 1 upon 6 plus 1 upon 4, which is equal to, I'm taking the product of these two, and therefore Rp will be equal to 24 upon 10, and that becomes our answer 1. Now we come to the second part, the total external resistance. So we will say total external resistance will be equal to, it will be this, that is Rp plus this. So it will be Rp plus 2 ohm, which will be 2.4 ohm plus 2 ohm, which will be equal to 4.4 ohm. And that is our answer 2. The total resistance in the circuit. So we shall write now number 3, total resistance in circuit will be equal to external resistance plus the internal resistance of the cell. So 4.4 ohm plus, see here we have the internal resistance, it is 0.6, so that will be added, which is equal to 5 ohm, and that becomes our answer 3. Number 4, the reading of the ammeter means current in the circuit. So we will say I is equal to, as we saw the formula, E upon R plus R, which is EMF is, look in the diagram, EMF is 20 volt here. So it's going to be 20 volt upon external resistance, this is here. So 4.4 plus 0.6, which will be 20 volt. Of course, I'll put bracket and put ohm upon 5 ohm, and that gives you 4 ampere. And that becomes our answer 4. The fifth subpart, current through 6 ohm. So we have to find I through 6 ohm. Now if you look at the diagram, the current over here in the ammeter, this is 4 ampere. So this current goes this way and it splits into 2 branches. I shall call this as I1 and I shall call this as I2. And then it goes like this and it completes the circuit. And so I need, in order to get the current here, I need the PD across these 2 points. So I shall now find out first PD across the parallel circuit will be equal to the current into the resistance of the parallel. So that will be equal to 4.4 ampere multiplied by RP is 2.4 ohm. Sorry about that. So we will have current through 6 ohm will be equal to this IRP, that is 4 multiplied by 2.4, these many volts because it's the PD, upon how much is the resistance? 6 ohm. And so you will have 4 multiplied by 6 goes 0.4 times, and so you'll have 4, 4, 16 and 1.6 ampere, and that becomes our answer 5. Let us look at our sixth one. Sixth one says drop in potential. So let us write it. Drop in potential. Now drop in potential was E minus V when we saw the formula, and that is equal to IR, that is the current in the circuit. Current in the circuit is 4 ampere multiplied by the internal resistance is 0.6 ohm, and so that comes to 2.4 volt. This becomes our drop in potential, and that is our answer 6. And the seventh one is terminal voltage. Can you see here terminal voltage of the cell? So terminal voltage, which is equal to V equal to how much? Now here we are going to use a simple formula. E minus V is equal to IR. EMF is 20 volt minus terminal voltage IR, which we found out here, 2.4. And so you will see V is equal to 20 minus 2.4. and so our terminal voltage V will be 20 minus 2.4, which is 20 minus 2 is 18, so 17.6 volts, and that is our answer 7. And so we have finished the review of our current electricity. So I hope that you are confident about the entire chapter and that you will be able to answer each and every question based on this chapter. I wish you all the best for your exams and thank you for watching.